Yeni bir çağın habercisidir milat. Bambaşka bir gözle bakmaktır hayata. Bir sayı, bir yazı, bir duyuş ve sözle ilim kapılarında. Bazen gözle görülmeyecek küçük sırlara vakıf olmaktır bilim ışığında. Umuttur, şifadır, keşiftir, mirastır milat, bir adım sonrasına. Geçmişten gelen mirasın takipçisiyiz. İlim ve bilim yolunda. Denizlere açılıyoruz mazinin dehlizlerinde, uçsuz bucaksız ufkumuzla. Doğanın gücünü göstererek güneş enerjisiyle yol alıyoruz. Tarihin gezindiği duvarlardan bugüne bakarak yol gösterici bir tavırla eğitimciler yetiştiriyoruz. Çocukken dahi yalnız bırakmadan geleceğimizi, insanımızı. Yine denizlere bakarak güzel sözleri takip ediyoruz. Bir şairin, yazarın izinde. Geleceği daha güçlü kılabilmek için çalışıyoruz ayrıca. Farklı formüller bulup fikirlerde yeni bir ışık yakarken, bazen de bir resim yansıtıyor aklımıza ayna olarak müziğin eşsiz çağrısını. Olmaya devlet cihanda bir nefes sıhhat gibi öğüdünü insanlık için hep diri tutuyoruz. Mülkün temeline olan inancımızla adalet terazimizi vicdanlarda kuruyoruz. Yedi bölge, 4 mevsim içinde tarihi de yaşatırken yenilikçi adımlarla verimliliği artırıyoruz. Teknolojik sanayi işbirliğinde ilklere imza atarak. Maddi yönümüzün yanına manevi hayatımızı da katıyoruz. İlmin yol gösterici ikliminde. İdare etmek için, büyüyen bir millet için sorumlulukla bakıyoruz her yana. Yeni bir yol, yeni bir buluş ve bakış ararken her tarafta yeni yapılarla yeni dünyanın kapılarını aralıyoruz. Sağlam kafa, sağlam vücutta olur sözünü anlatıyoruz burada. Burası geçmiş ve geleceği birbirine bağlayan milat. İlk hedefimiz Akdeniz'dir emrini ölümsüzleştiren kabul. Burası medeniyet. Burası 9 Eylül. Yeni bir çağın habercisidir milat. Bambaşka bir gözle bakmaktır hayata. Bir sayı, bir yazı, bir duyuş ve sözle ilim kapılarında. Bazen gözle görülmeyecek küçük sırlara vakıf olmaktır bilim ışığında. Umuttur, şifadır, keşiftir, mirastır milat, bir adım sonrasına. Geçmişten gelen mirasın takipçisiyiz. İlim ve bilim yolunda. Denizlere açılıyoruz mazinin dehlizlerinde, uçsuz bucaksız ufkumuzla. Doğanın gücünü göstererek güneş enerjisiyle yol alıyoruz. Tarihin gezindiği duvarlardan bugüne bakarak yol gösterici bir tavırla eğitimciler yetiştiriyoruz. Çocukken dahi yalnız bırakmadan geleceğimizi, insanımızı. Yine denizlere bakarak güzel sözleri takip ediyoruz. Bir şairin, yazarın izinde. Geleceği daha güçlü kılabilmek için çalışıyoruz ayrıca. Farklı formüller bulup fikirlerde yeni bir ışık yakarken, bazen de bir resim yansıtıyor aklımıza ayna olarak müziğin eşsiz çağrısını. Olmaya devlet cihanda bir nefes sıhhat gibi öğüdünü insanlık için hep diri tutuyoruz. Mülkün temeline olan inancımızla adalet terazimizi vicdanlarda kuruyoruz. Yedi bölge, 4 mevsim içinde tarihi de yaşatırken yenilikçi adımlarla verimliliği artırıyoruz. Teknolojik sanayi işbirliğinde ilklere imza atarak. Maddi yönümüzün yanına manevi hayatımızı da katıyoruz. İlmin yol gösterici ikliminde. İdare etmek için, büyüyen bir millet için sorumlulukla bakıyoruz her yana. Yeni bir yol, yeni bir buluş ve bakış ararken her tarafta yeni yapılarla yeni dünyanın kapılarını aralıyoruz. Sağlam kafa, sağlam vücutta olur sözünü anlatıyoruz burada. Burası geçmiş ve geleceği birbirine bağlayan milat. İlk hedefimiz Akdeniz'dir emrini ölümsüzleştiren kabul. Burası medeniyet. Burası 9 Eylül. Yeni bir çağın habercisidir milat. Bambaşka bir gözle bakmaktır hayata. Bir sayı, bir yazı, bir duyuş ve sözle ilim kapılarında. Bazen gözle görülmeyecek küçük sırlara vakıf olmaktır bilim ışığında. Umuttur, şifadır, keşiftir, mirastır milat, bir adım sonrasına. Geçmişten gelen mirasın takipçisiyiz. İlim ve bilim yolunda. Denizlere açılıyoruz mazinin dehlizlerinde, uçsuz bucaksız ufkumuzla. Doğanın gücünü göstererek güneş enerjisiyle yol alıyoruz. Tarihin gezindiği duvarlardan bugüne bakarak yol gösterici bir tavırla eğitimciler yetiştiriyoruz. Çocukken dahi yalnız bırakmadan geleceğimizi, insanımızı. Yine yine denizlere bakarak güzel sözleri takip ediyoruz. Bir şairin, yazarın izinde. Geleceği daha güçlü kılabilmek için çalışıyoruz ayrıca. Farklı formüller bulup fikirlerde yeni bir ışık yakarken, bazen de bir resim yansıtıyor aklımıza ayna olarak müziğin eşsiz çağrısını. Olmaya devlet cihanda bir nefes sıhhat gibi öğüdünü insanlık için hep diri tutuyoruz. Mülkün temeline olan inancımızla adalet terazimizi vicdanlarda kuruyoruz. Yedi bölge, 4 mevsim içinde tarihi de yaşatırken yenilikçi adımlarla verimliliği artırıyoruz. Teknolojik sanayi işbirliğinde ilklere imza atarak. Maddi yönümüzün yanına manevi hayatımızı da katıyoruz. İlmin yol gösterici ikliminde. İdare etmek için, büyüyen bir millet için sorumlulukla bakıyoruz her yana. Yeni bir yol, yeni bir buluş ve bakış ararken her tarafta yeni yapılarla yeni dünyanın kapılarını aralıyoruz. Sağlam kafa, sağlam vücutta olur sözünü anlatıyoruz burada. Burası geçmiş ve geleceği birbirine bağlayan milat. İlk hedefiniz Akdeniz'dir emrini ölümsüzleştiren kabul. Burası medeniyet. Burası 9 Eylül. Yeni bir çağın habercisidir milat. Bambaşka bir gözle bakmaktır hayata. Bir sayı, bir yazı, bir duyuş ve sözle ilim kapılarında. Bazen gözle görülmeyecek küçük sırlara vakıf olmaktır bilim ışığında. Umuttur, şifadır, keşiftir, mirastır milat, bir adım sonrasına. Geçmişten gelen mirasın takipçisiyiz. İlim,
Welcome to the first session of our symposium, International Symposium of Advances in Computer Science. And I want to introduce you our Dean of Faculty, Engineering Faculty, Professor Dr. Turgay Onaykan, for the first speech for the opening ceremony. Please, Professor.
Thank you. Dear delegates, colleagues, students, and guests, good morning, ladies and gentlemen, fellow speakers, and good morning to our audience joining us online from around the world. As you know, we are celebrating the 100th anniversary of our republic. We are very glad to welcome you for the International Symposium on Advances in Computer Science, which will be held online from 26 October 2023 in Izmir. Computer science is a rapidly evolving field, and there have been numerous advances in various areas. Last 5 years, many more advancements have likely occurred. Here are some key areas of advances in computer science up to that point: artificial intelligence and machine learning, quantum computing, blockchain technology, cybersecurity, data science and big data, cloud computing, autonomous systems and robotic process automation, etc. This symposium will be a very fruitful space for computer specialists, We all understand the importance of science, technology, and innovation in our day-to-day lives and the ways in which they are transforming the world. For these reasons, I find the outputs of this symposium very valuable. I hope this symposium will open new doors for new research and technologies. Many thanks to delegates and to all persons who worked in this organization. I believe that by participating in this symposium, we are in the right place and the right time. Together, let us accelerate the exchange of ideas and scaling up of good practices. Thank you so much.
Thank you very much for the opening ceremony, for the opening speech, Professor. We will send you to your meetings from here, and we will start with the first presentation with the first speech. We will have 5 speeches from 5 different countries, and I want to repeat our program for the first session. In our first session, we will talk with Professor Dr. Vladimir Radevski from the University American College Skopje from North Macedonia, and he will introduce us his valuable thoughts and his research on open AI in education and challenges and opportunities. He has many research and he has many new ideas, and I think he will explain us many things about the open AI, and he will give us new visions about the open AI for using in education. And after that, Professor Dr. Stephen McGough from Newcastle University from UK will be our guest, and he will talk about the need for more and novel data sets to help in identifying the best deep learning network. He will join us from United Kingdom, and he will also explain us preparing new data sets for extending our experience on deep learning networks and deep learning management. And in the session 2, after the lunch, we will talk with Julian Wilson from Freedom Pay from United States of America, and he will talk about the social things on business things in computer technologies, turning ideas into businesses in computer technologies. We will talk about from research to business. And after that, Assistant Professor Dr. Zerrin Yumak will join us from Utrecht University from Holland. She is also one of our graduates, and she will talk about socially intelligent virtual humans in XR and games. She's working on VR and AR, and she's head of a laboratory in Utrecht University, and she will explain us her experiences on virtual humans and about the extents and about the advances in virtual reality and other things. And at the end of the symposium, Dr. Jan Avshar will join us from Technical University of Denmark. He is working in National Institute of Aquatic Resources from Denmark, and he will explain us digitalization of fisheries using computer vision and AI. He has valuable research on AI and artificial intelligence and working on computer visions, and he will try to explain us different versions, different applications of computer vision and AI and in fisheries in the real world. We need 5 minutes to prepare our first session, the first presentation, and we want just 5 minutes for preparing our first presentation, and we will be back in 5 minutes. Thank you for joining us.
Dear colleagues and friends, good morning. My name is Vladimir Radevski, and I'm very happy to be part of this Newcastle University International Symposium on Advances in Computer Sciences. The topic of my presentation will be open in brackets, AI in education, challenges and opportunities. The subtitle is more speaking about the presentation, those machines that mess up our minds. I hope that we will have interesting half hour together and maybe some discussion or questions later on. But before starting, please let me send you greetings and regards from Skopje, which is Üsküp in Turkish language. And first of all, I would like to extend my gratefulness to the head of your department, Professor Derya Birant, with whom we have collaboration and friendship relations since 2005. I use this opportunity to congratulate her for her position of taking the lead of the department. Sorry. Since I was closely following your department in the last maybe 15 to 18 years, I'm sure that the Derya will successfully take the lead and include inventive, innovative news to the life of the department. This collaboration and this meeting with the respectful Newcastle University and Department of Computer Science started with the cooperation with very respected Professor Alp Kut, with whom we maintain, since the first meeting, we maintain strong relations in collaboration, in projects, in committees. So it is through his linkage that I was able to meet many friends and to experience common publications in international conferences. Just to mention a few of the colleagues that I remember with happiness from your university, Professor Yalcin Çebi, Ulaş Kokten, Özge Kart, Ferishtah Dalkılıç, Gökhan Dalkılıç, Semih Hutku, Yunus Doğan, and surely there were other young colleagues that I was not able to mention here. I want to send greetings and regards to all of you. Okay, let's return to our topic today. In the title of the topic, there is a most used word, especially in the recent months and years, artificial intelligence. And it is, as you know, a very vast topic of discussion. And we can speak with hours and even with semestrial long courses about the history of AI, the main areas of AI research, applications of AI, even consequences and experiences, how AI changed till now the world and the research world, but also our societies and the world in general, because it will be really impossible to name some of our, at least online or IT-related activities that don't include any AI algorithm or implementation, maybe in the most hidden way, up to very explicit one. This list is long of the topics of AI, and nowadays it ends with two very unknown and very unclear issues. Some of researchers are speaking about approaching to the achievement of theory of mind, which is a questionable statement. And as ultimate future that we are still far from is so-called self-aware AI, where the AI systems will be able to improve or to have a feedback on themselves, to speak with psychological terms, consciousness about themselves, etc. So in these vast areas of possibility for discussion and reflection in the scientific world, I want to recall few basic positions that were very actual since recently, and that created the fundamentals of AI as area. So the most basic definition is that it is intelligence exhibited by machines, although we still don't have a perfect definition for what intelligence is. And basically, the activities or the behavior of these AI systems were defined as flexible rational agents that perceives the environment, so receives some inputs from the environment, whatever it is, a picture, a signal, anything detected, and takes actions that maximize its chances of success at some goal. This chance of success can be recognition of something, or getting up with a right decision about some decision, etc. Traditionally, these systems were built to mimic the cognitive functions that humans associate with their human minds, such as learning and problem solving. So we were speaking about systems that can learn to play something or to do some activity, or to solve a problem as we humans are solving. And based on these three traditional postulates, problems and goals historically were defined in various sub-areas: in reasoning, in knowledge, presentation and usage, in planning, in learning, in natural language processing and communication, in perception, in ability to move and manipulate objects, etc. All this was based on the fundamental claim that the human intelligence can be so precisely described that a machine can be made to simulate it. So during pretty much a long and rich history of research in artificial intelligence, we were mainly trying to understand and code the human intelligence behavior, the evidence of human intelligence, and to describe it in a machine code, to develop correspondent models, and then to let them behave as the humans would behave. But in 2016, something dramatically different, it seems, and by my opinion at least, something dramatically different happened. A Google product, AlphaGo, in 2016, Google announced that have created a machine in the system, a so-called deep neural network or deep learning algorithm that won the actual world champion in the game AlphaGo, which is South Korean game, a very popular game in South Korea. It was not the first time that machines beat the humans in some activity or in some especially gaming activity. We know about the IBM products of chess playing, etc., etc. But something that was very new with this event in 2016 was that this artificial intelligence model was not taught, didn't learn from rules of the game, but rather he was programmed, or a system was made, this deep learning network was made, that imitates the human reasoning on the basis of evidence of reasoning. So, roughly speaking, they supplied enormous amount of games on the AlphaGo, and without giving the formal description of the rules of the game, they put this neural network in learning process, so she could imitate the human reasoning on the basis of evidence of reasoning. This is a fundamentally new approach that resulted with a very successful system that became very popular, and by my opinion, it is one of the milestones of the recent development of artificial intelligence. And basically, it is based on a system that is a complex neural network based model for reinforcement supervised learning. In the following slides, we will a little bit go deeper to this terminology in order to understand why it is so important. So after passing through the history and through the way that we wanted to code and to represent our knowledge and skill for problem solving, we are coming to a model developed by Google that takes another approach in building the power of its system. So very often, young students or young colleagues, novices in machine learning and in artificial intelligence and not to speak about the people that are not in IT, when you will mention that you have a system that can learn something, they have also attacks of panics. Oh, how do you mean it can learn something? This is magic. This is so complex, etc., etc. Simply, there are many known models of programming codes that can be repetitively run over on the machine. In each repetition of running can modify their parameters according to the optimization of some output function, and we are knowing them in terms of simple neural networks or deep learning neural networks, where by deep we understand the number of layers, of hidden layers of these programming models that are able, without entering into details, these programming models are able to modify their running parameters through one process called the process of training, and achieve one level of performance that exhibits something that is very close to human intelligence. Normally, the people that are working with these models, especially in the past, now it is a rather automated process, and you can get a neural network and train it with some given data set, but it is rarely something like these nice color pictures that are coming up in our journals or in our internet pages. It is really painful and very complex process of training and implementation of mathematical formulas. What is important at this stage to say that these systems based on neural networks, deep learning, are mostly, not to say even by definition, unexplainable. We have in the recent years explainable and unexplainable AI. What is going on in the neural networks? There is a huge contradiction between the superpower and the performances that are exhibited by these models and the ability to explain why this answer was given by the neural network. And in the further slides of our presentation, I will want to underline several times that especially speaking about the last ChatGPT model that we want to examine a little bit in this presentation, we are in an unexplainable area of using of AI. It means that if a system detects that according to these medical results, the patient is 98% probability of having cancer, we will not be able, or these systems will not be able, in contradiction with their accuracy, will not be able to clearly list out the path of reasoning that lead to this conclusion, which is one important fact, by my opinion. So finally, in November 30, so almost 1 year ago, a private company, OpenAI, released for a public free usage something that they called ChatGPT, with the full name of Generative Pre-trained Transformer, which is basically a large language model chatbot. And since January 2023, it is the fastest growing consumer software application ever present on the market. Each of the following months after January, we experienced some new features, new releases. In September 2023, we received information that now this system can see, hear, and speak. It means that we can communicate with him not only with text. And there is also a set of other applications like DALL-E 2, Jasper, Copy AI, the first one for images, generating images, working with text. And the main one, however, is the ChatGPT, actually in ChatGPT 3 version and with paid version on ChatGPT 4 or ChatGPT Pro. What is the identified experience that humanity had with this application since January? I mean, we are speaking about 10 months of experience. I will state it like this. We are all amazed. We speak among friends about experience that we had while we first tried this chatbot. We are delighted. We communicate with it anything, questions about history, about love, about private lives, about businesses, about everything. And we retell our experiences with enthusiasm to our friends. Oh, you know, I asked this question. Do you know what answer I received, etc. And with fear, because we are for the first time, we are faced with a computer system that speaks with us on a natural language and can give quite reasonable and meaningful type of sentences. But this system, after this 10 months of experience, this system was massively manually influenced on their answers. So that is something that I want to point out very strongly in this presentation. And we are faced with a system that always answers kindly, with pleasant phrases, mostly positive, and of course, as politically correct as possible. Why I'm mentioning this? Because I know that a great majority of the listeners of this presentation today will be future IT specialists, IT engineers, and probably there will not be a job position or a profession in the IT world that will not have some connection or some relation with those kind of AI products. And obviously, we will speak about profitability. We will speak about changing the ethics of job, the erased profits, etc., etc. But if you put a very childish poem, and if you ask ChatGPT what kind of poem this is, the first reply will be, "Oh, this is beautiful poem about I don't know what." If you are a novice in poetry, and if this poem, ChatGPT says that it's a beautiful poem, you risk to get a really completely wrong opinion about what is beautiful and what is not beautiful in the poetry. So my first problem here is why we built a machine that answers always kindly, with pleasant phrases, mostly positive, and as politically correct as possible. In order to go back and to see and to discuss why these systems behave in a way they behave, I will just point out two important, by my opinion, things in the building and in the way these systems work. So let's recall that these systems communicate with us in natural language, which is psychologically very important for our attachment to them and for our evaluation of their ability. It appears that when we receive textual information about something, we have immediately changed value position in evaluating those systems. It's free. We will see up to which extent. And everybody that tried it knows that you must get registered in order to try the ChatGPT 3 free version. And there is at the moment one feature that is that it remembers all the conversations and interactions that we made with him. There is no way to erase our history of interaction with ChatGPT. So GPT stays, P in GPT stays for pre-trained model, this deep learning neural network that I was mentioning. In the product like ChatGPT, obtained little bit modified way of implementation. And just to point out that what I will say in the following 4 slides, it is information that is available on the internet. We are speaking about corporate property. OpenAI is not public, it's not ours, it's corporate property. So we are able to obtain information what is going on besides the interface that is available to us with the machine only through secondary type of information available on the internet. And I have gathered some information from some respected bloggers, some companies that are offering ChatGPT integration in their systems, so they are obliged to explain what is going on behind, and some publicly available research papers, for example, like the research paper from 2017 explaining some of these algorithms. So in the classical training of neural networks, we have a supervised learning model when we present to the neural network data sets with parameters of some phenomenon and the class of that phenomenon. So we are saying this image is of person XY, this image is on person XY, Y1, and etc. etc. The system is trained in order to behave in a similar way when I will show him an unknown image. In this case, in the case of ChatGPT, the available labeled data sets for supervised learning were not enough. I speak worldwide available, are not enough to train the model with the performances, with the level of performances that wanted to be expected. So something that happened is that the system was first passed through the system through the phase of generative pre-training, which is basically based on a few ground rules and fed enormous amount of unlabeled data. This unlabeled data, I have listed here some of possible resources: a Common Crawl, a web text tool, Books 1 and Books 2, Wikipedia, Persona Chat with different percentages. All these means of text were first built into the presented to the system in order to create a deep learning neural network, which is mostly unsupervised way of learning. With the other words, forcing the system to create its own relationships on unlabeled data. And obviously, such trained deep learning neural network was not able to give answers of answers of prompts by the users in a interesting or usable way. So that is why this the further on the second phase of the secret of powerful comportment of GPT is the T letter of the word, which is so-called transformer architecture, which was scientifically published in 2017. And whoever worked with natural language processing models, he knows that the text is separated by chunks of text, even smaller than words. And then comparison and sequences are studied in most of the natural language processing models, somehow to achieve something similar to the game what word follows after these 5 words. But the transformer architecture, the innovative part of transformer architecture, is in the formalization of the input text in tokens. A token can be part of text or even part of a word, in which an input text is separated. And one thing is this tokenization of the input text, and second thing is the manipulation with these tokens. Unlikely the previous experience of sequential manipulation, like which word follows after this word, the characteristic of transformer architecture is that these vector comparison calculations are done over extremely large data inputs, with reported 175 billion parameters for ChatGPT-3. We even don't know for ChatGPT-4 how many parameters. So the first phase after this network was passed through the deep learning process was to in a parallel consideration what ChatGPT authors are advertising as self-conscious way. It doesn't have anything of self-consciousness, but this token separation of the text, instead of being examined in sequence one after each other, with the parallelization algorithms, the training is able to be performed in parallel over all tokens extracted from some text. These apparently added a new superpower of the quality of the closeness of the vectors extracted from the text. Now, this is some slides, presentation of the image presentation of the 2 ways of training delivered by the SEMrush blogger, which explain this and the following phase of the fine tuning. What is important is that after our network was built on this great amount of data on internet, there was a process of human, I think that I have it somewhere, the name of the algorithm was reinforced human feedback, something like that. So a huge amount of humans was involved in refining the answers of the so-trained deep network. For example, by taking into consideration 2 possible outputs of the models and giving back the evaluation, which one is better, which one is worse, and putting back that information to the trained model in order to improve the efficiency. So more in details, replies of the prompts were refined by huge human engaged users before it went public. For example, out of, you see in the step 2, out of several possible outputs of the network, the humans were asked to prioritize or to sort the quality of the answers, and this feedback was given back to the network in order to behave in a better and more successful way in the future, which was again promoted by the ChatGPT owners as proximal policy optimization, PPO, at the end of the slide, means proximal policy optimization, which is in fact a result of this process of human interaction with the system. Okay, how this was then, this technical part and this computer science part, what kind of life and changes provoked in the world of usage of this system. Noam Chomsky in March 2023, 6 months ago, expressed one very powerful concern about after the experience of this, I will speak in general, ChatGPT, but I mean all the models that are built in a similar way, by saying that we fear that these kind of systems will degrade our science and debase our ethics by incorporating into our technology a fundamentally flawed conception of language and knowledge. Pay attention now. This is some of the things that we are speaking rarely when we speak about this ChatGPT. As I said before, most of you and most of us are involved in usage and in explanation of ChatGPT like products. The profit is surely on the side of more significant usage of these models. But what we are doing with, and I think that the principal tasks of university existence is the rush for the truth, for the values, and that is why I choose to speak about this topic in besides other things. So while using these kind of systems, we are changing our conception of language and knowledge. They will be very useful in narrow domains and will exhibit complete different reasoning and use of language vis-a-vis how humans reason and use the language. Finally, the human mind is not like ChatGPT, a lumbering statistical engine for pattern matching. Learning versus memorizing, in this case, not facts, but way of elaboration. What is the new thing after 2016 with this kind of systems is that we didn't taught them the rules of the game, but we showed them various games. So the ways of elaboration. And the conclusion of Noam Chomsky was that given the amorality, false science, and linguistic incompetence of these systems, we can only laugh or cry at their popularity. If this reasoning on the deep learning algorithms is imitation of human reasoning on the basis of evidence of reasoning, let us see what kind of evidence of reasoning are available for the systems like ChatGPT. Available data sets on the web, besides everything what can be crawled and given in the system for unsupervised part of the learning. Obviously, in the programming world, you will see that the behavior of ChatGPT is almost perfect, because you have thousands of codes available even before ChatGPT through other systems that were made to support code production. Now we need to make distinction between programming and code production. If we are speaking about code production, so the results of this kind of machines trained on already existent working sets of coding will be uncomparable with any human with potential. Medical evidences, especially in the developed medical care countries, you have very nicely evidenced history of medical evidences and outcomes, not to speak about legal and policy documents. That is why these systems are very powerful and successful in automatic and court statement production. Scholarly resources, that is why universities are challenged with the absolute incapacity of dealing with homeworks nowadays. How you will check a homework when you know that this homework can be automatically produced in a very, very powerful way. So these available data sets are one big source of explanation what is going on with our systems and why they are like this. And secondly, these massively human interfered adjustments, we know that they were done as outsourced. Some sources claim that they found engagement of people in Kenya and in other underdeveloped countries for less than $2 per day payments. This human interaction with the system was done. What is more striking me is why they are extensively non-critical and with positive approach. Our lives and our world is far from being only a place for positive approach statements and for extensively non-critical and politically correct words to say. So writing and speaking and nice storytelling is not thinking. So I want to point out this here because I am afraid that with more and more relying on writing automatism of these systems and of hearing of their stories, which are perfectly done, nice storytelling. You can order a story in the style of Shakespeare. You can order the story in the style of the biggest brains of the human history. But all these things are not thinking how we solve problems. So the question is here, who set these ethical standards of what we would or would not like to hear from our new online friend? All of us, experts in IT and working with IT products, we will work with them, we will use their replies, and we need to ask ourselves, who set these ethical standards of what we would and would not like to hear? If we compare this industry with the industry of production of food, medical products, even news in the media, we will see that in these three areas, go and try to register one new medicament in the marketplace of Turkey or anywhere in the world. It is a painful, long-lasting process. Even these vaccines against COVID-19, with all urgencies and not respecting the regular way of developing vaccines, needed 6 months to a year to get developed and put in the market. Now we have this guy, this storyteller, that is not limited by any of this. We are communicating with him. We are asking questions, we are receiving the answers, we are submitting those answers to our professors as our work or to our clients in the companies, and nobody regulates it. Because we didn't regulate also the usage of smartphones in the schools, and we all know the bad influence on the process of learning, access to social networks and specific platforms. Again, we will not be able to regulate as humanity. Addictive computer games, we only know some cases where they are limited to 2 hours or to 1 hour per day. But again, this is nothing vis-a-vis what is going on with the... And me personally, I'm afraid that we will not be able to regulate our ever-ready, talkative, and highly intelligent friend for the same reason. Because we would not want to do. We would like to have a program always available on our mobile phones where we can ask questions and we will receive nicely written in our own language phrases. So there are different kind of opinions expressed on the ever bigger usage of generative pre-trained transformer in the public life. My statement is that it is a threat before opportunity. First, because it is a corporate property, it is not ours, not public. We don't know what kind of algorithms and what kind of training it was used there. We interact through an interface and everything is recorded. If we follow how the institutions and the world established organizations try to regulate the usage, we will see that once again, the profit-making companies, the corporate business learning prevails vis-a-vis the efforts of the institutions. I was part of the UNESCO ethics on artificial intelligence group that resulted with, after 1.5 years of consultation with the top experts in the world, in 2021, UNESCO published the ethics on artificial intelligence usage. This will remain a document that is a general guidelines, orientation, etc. But in the meanwhile, we will have broader and broader usage. There is a difference between European Union and United States regulations in this regard. However, in the United States environment, this kind of softwares is allowed as far as it follows some principles of so-called fair usage. In European Union, they are the data protection and property laws are meant to be more strictly imposed. The last example is from May 2023, when Facebook was fined 1.2 billion euro by European Data Protection Board for abusing or not proper usage of the property data. So in the last 2 minutes of my presentation, I want to point out that if we see what kind of changes various other IT innovations brought to the world in 83 with the internet, 94 with the first internet cafe, 98 Google, 2004 Facebook, 5 Amazon Prime and Amazon Web Services, Apple iPhone 2007, Google Chrome browser 2008, 2010 Instagram. In 2016, a very respectful author of the Guardian newspaper wrote something that was really striking. Social media hasn't just swallowed the journalism, it has swallowed everything. It has swallowed political campaigns, banking systems, personal histories, leisure industry, retail, even government and security. Can you imagine if in 2016 we were able to listen this kind of statement about social networks usage? What we will experience with massive usage of ChatGPT that generates over reported $80 million per month revenue now, and with across over 10 billion all-time visits. I think that there will be extended usefulness and practical usage in a narrow and appropriate domains of the systems. And I'm afraid that we will be faced with dangerous misuse and focus of efforts in the others. As Yuval Noah Harari stated in Economist in 2023, the fears are that AI could even form intimate relationships with people and change our opinions and worldviews, which is one step more dangerous than the social networks influence that we saw in the previous slide. People may come to use a single AI advisor as one-stop all-knowledge oracle. You will travel 3 hours in your car, you are alone, you will start a conversation with your AI advisor. Who knows where he will bring your mind? I mean, hopefully to bring your mind in some positive way, but we are not sure. What will happen further on when AI takes over our culture and begins producing stories, melodies, laws, and religions?
I hope we're okay now. I'm sorry about the problems. That's a technical problem if you do this on techniques, and we may experience also some technical issues. I had a question to Professor Radevski about the economic situation for people around the world, around the whole world. We have last 2 minutes. Can you summarize your last answer, Professor, if you are able?
Yeah, I mean, to reply with the argument of this question, I will recall the chart of ethics of usage of AI issued by UNESCO in 2021. It is clearly stated that this kind of system, if not regulated otherwise, they will make the gap between rich and poor or less rich countries even bigger. There will be slight change in the opportunities, so the people will be able to work online on a distinct measures and have access to the technology. But globally, this will gather more profit in fewer points of richness, and will not tremendously improve the overall economic situation in the world, especially in the poor countries.
Thank you very much for your reply, and once more, I'm very sorry because of the technical issues. I had also one more question about the change of education after AI, after using AI. Should we change the objective of education, or the way of education, or evaluation methods of education? I had also
Everything.
That's
You
it.
know, you know, because you are one of the leaders at your university that was aware of these Bologna declarations and need for evidence for evaluation, or how many quizzes, how many homeworks. It should not be only the grade issued by a professor because it may be biased. Show me how many homeworks, how many quizzes. Now it is everything going back and saying, okay, we cannot justify any work of the students outside of the classroom. So it is the professor to judge, is it right or not. So, the only recommendation that I can see from this experience is the place and the role of the professor will be more responsible and more important in the future. Unlikely what it looks like, the people will get trained by ChatGPT to program. No, this will not happen. The real training will again have to come from the professors. The professors will have to change the paradigm of learning and teaching, because the students will be able to find answers of their questions more easily through ChatGPT. But the real knowledge and the deep understanding of the things and the developing of the thinking and reasoning is more in the hands of the professor now than it was before.
Thank you very much, Professor Radevski, and we will try to go to the next presentation. I want to introduce Professor Dr. Stephen McGough from Newcastle University with the presentation of the need for more and novel data sets to help in identifying the best deep learning networks. We may start the next presentation. Thank you.
Right. Hello. So I'm Stephen McGough. I'm a reader in machine learning at Newcastle University. And I'd like to talk to you about the need for more and novel data sets to help identify best deep learning networks. A bit of a title, but hopefully I'll be able to explain it as I'm going through. And I'll also explain why there's that odd picture of me down there. So I'll give you an outline of the talk, which is we're going to talk first of all about deep learning, and I'll give you a little bit of a primer into that. I'll then give you a primer into neural architecture search and what that's all about. I'll then talk about the current problems with neural architecture search, and then I'll talk about what we're actually doing to try and deal with that. So, deep learning primer. Hopefully everybody's aware of what artificial intelligence is, machine learning is, and deep learning is. And this is just a slide to sort of illustrate that. But I'm going to continue straight away because I do believe everybody here should have some sort of notion of what each of these terms is. So obviously, machine learning versus deep learning. Machine learning requires some sort of expert normally who learns how to extract the features from a data set. So if we're wanting to do images of cats, they would learn how to pick out certain features from those pictures to then pass into a machine learning process. Whilst deep learning provides a network where you can just take the raw data, the raw pixel values, and actually come up with some sort of network which will do everything for you. And so this was seen as a democratization of machine learning. It removes the need for having an absolute expert every time you try and do these sorts of things. So I'll give you, as I say, a very shallow and quick introduction to deep learning, just in case you haven't seen these sorts of things before. And we'll talk about how we actually build this up. So obviously we start from data. Now, data can come in any shape or form, but for simplicity here, I'll talk about just a 1D array of values, and they're my X values down the side of the screen there, X1 to X6. And then from that, we could build up a system where we sum those values together and get an output. Now, obviously, that will give us a sum of all those values, but that's not particularly intelligent and doesn't do very much. So, for example, what if X1 is much more significant for the problem we're trying to solve than X4? So we get around that by having weights within these systems, and we multiply each X value by its associated weight, and then we sum those values together. But that's still not particularly clever because, again, we're just linearly combining these values. We also had in what's called a bias value, which is a constant fix, which may shift the values into the sort of range that we want to see them in. But again, this is still not particularly clever because it's still just linear operations. So to get around that, we have the notion of an activation function. And this is a nonlinear operation which is applied to the output of our single neuron here and allows us to do much more complicated things and allows us to learn much more intelligent systems. And there we go. So what makes this neuron clever? Well, it's the right values of the weights and the biases, and it's by training the network by passing huge amounts of data through it. But obviously, there's a very small amount of stuff you can do with just a single neuron. So to deal with that, we build up networks with a huge number of these neurons in them. So we'll take that single neuron there that we've just been talking about, and we'll put it together as part of a larger network. And these larger networks have things such as input layers, output layers, and hidden layers in the middle. And often we don't bother drawing the lines in because, as you could kind of see in the previous slide, there was a lot of lines between them, and that was for a fairly small network. But you can implicitly understand that there should be the links there. And we often call these multi-layer perceptrons, fully connected layers, or dense layers. Now, obviously, in terms of deep learning, there are lots and lots of other types of neurons that you can have out there. You can have convolutions, pooling, transformers, recurrent, all these sorts of different types of layers within your network. But for the purposes of this talk, I'm just going to stick to that because at least you've got something, if you've never been involved in deep learning before, to understand these sorts of concepts. Right. So you might ask the question, why is this deep learning? And it's all due to the fact of the depth of the networks. The network I've shown you there had 4 layers to it, but in a real network, you'd have tens, hundreds, thousands of layers. And these networks are often referred to as models. And why are we doing this now? Why is this sort of prevalent? I mean, the whole idea of neural networks was first founded back in the 1980s. And it's basically because nowadays we have the data available and we have the compute power to be able to deal with these sorts of things. And I'm just going to talk about one other activation function, which is the softmax activation function. And this is because it's different to the other ones. All the other ones are just a nonlinear value that's applied to the output of a single neuron, whilst the softmax is applied across all outputs. And each of the outputs will be in the range of 0 to 1, and all of them sum together. And effectively what we do is we take the exponential of each of them, and then we divide by the sum of all the exponentials. So if I have a thing down the bottom there with 3 outputs, we take the exponential of each of them, we take the sum of the activations, and we come up with our softmaxes. And hopefully, if I've got my maths right, they should add up to 1. And what we'd normally say is the 0.041 is the largest value, and so therefore that's the output of the network. And that's often used when you're doing classification. So you'd say, well, whatever the output for this one is, this is what the network thinks the output is. Right, so that was a very, very short, very, very quick introduction to neural architectures. I'm now going to talk about neural architecture search and just give you a little bit of an introduction to that. So in terms of that, let's get started. So the thing is here is, as you can imagine, there is an infinite number of possible networks. And the question comes, which is the right network for my particular problem? Okay, there are thousands, if not millions, of papers out there where people have proposed networks. They've tried them on different data sets. They've got results. They've maybe shown that for a particular data set, their network gets a better result than somebody else's network. But obviously, there are an infinite number of these networks, because any time that you're saying, you've got a bunch of layers and a bunch of different components within each of these layers, you could obviously have an infinite number of these. And also, the thing that I didn't talk about in the neural architecture primer was the idea that you could have links that go between not just one layer and the next, but you could actually skip over layers and so on and so forth. And the problem is here is there's a theorem called the no free lunch theorem. And that basically states that there's no network, no solution, which is best for all problems. So you might have a network, you might know about ResNet, you might know about ResNet 50, and you might go, well, ResNet 50 will be good for any problem I might have. And, it might be reasonably good, but it probably isn't going to be best, or will definitely not be best for every possible network that's actually out there, or every possible data set that's out there. And so what we really want to do is we want to find the best for each problem. And obviously, because there are an infinite number of data sets and an infinite number of networks, we can't work on the assumption that humans could necessarily find those. And also, it brings us back to this problem. So originally, deep learning had this wonderful sort of mantra that effectively, by doing this, we get rid of the need to have this huge expert who was an absolute guru in machine learning. If we're now saying, well, we actually need this guru to come back to tell us which is the best network for our problem, then we're kind of breaking this thing of moving away and democratizing machine learning. So we want some sort of automated process which can actually do that. And that's what we talk about when we talk about neural architecture search. So neural architecture in a nutshell is automatically identifying the best neural architecture for a given set of data under a given set of requirements for a given problem. So this data is obviously the data set you have, and it could be whatever you have as your problem. And the set of requirements can include things like the performance of it. So what is important to you? It might be that accuracy is important to you. It might be precision. It might be recall. It might be things like R2. It could be that you're working on embedded devices, and therefore the memory footprint is important. You can't have a network which will require more than 0.5 megabyte of RAM to actually store, because that's all the memory you've got available to you. It could be the amount of execution time it takes to actually do a prediction. If you're doing real-time prediction and you need to have your results in, 10 milliseconds, having a network which is absolutely brilliant but takes, 0.5 second to actually get your answer is, not very good. And obviously other things like training time, how long it actually takes you to train your network. Now, again, with this infinite, search space and this infinite number of, networks that you can possibly have, the longer you search, the more likely you are to find a better network. But obviously the problem with that is it could take you too long. Obviously in these sorts of cases, the amount of time it takes you is problematic, but obviously the cost for actually using the computing power for that time could be actually detrimental for you. So when we talk about NAS, we talk about the process of NAS, which is neural architecture search, and we talk about the different parts of it. So the first part of it is the search space. And this is all the possible networks that we're going to consider. Obviously, we start off with an infinite space, and normally one of the first things we'll do under these circumstances is we'll turn around and say, given we've got an infinite space, let's cut it down to just a subset of that infinite space that we can actually actively search over. So I've got an example here of just a bunch of networks that you could obviously be using for your search space. Now, obviously, this is a very, very small search space, and a real search space would contain thousands, if not millions, of different networks, and you would be able to actually search across those networks. The second thing you need is a search policy, and this is effectively the neural architecture search code. And this is how you will actually move around your search space to actually find the optimal network. And this often comprises of two main phases. There's the search phase, which is how you actually find a good architecture. So, you might start off with the architecture on the left there. That may then prompt you to try the architecture on the right. And then that might prompt you to try the central network there. And then once you've identified what you think is the best network, you will actually train up that network and see how good a set of results you actually get from that network. Now, it's a bit of a sort of inconsistency to say it's actually a search phase and evaluation phase, because some approaches actually do the search and evaluation in the same step. But in general, we tend to think of it as two separate steps. Oops. The next phase is to actually think about, or next part is to think about the data policy. So you've got this data that's coming in. Again, it's a limited set of data. It won't be every single possible data item that you could have within your space. And this is where you would think about possibly what data augmentation policies you might use across that data. So there's all sorts of things you can do here. You can brighten, flip, crop, change the perspective, add noise, occlude items, rotate, contrast, blur. And they are just some of the examples of things that you can actually do to actually augment the data. And we often include data augmentation in here because it's a very, very subtle difference in terms of a lot of these augmentation approaches you can actually build into the structure of your network. And therefore, if you don't include them in here, then you're kind of reducing your search space and you're reducing your possibilities. So although, some people do say that, sort of data augmentation isn't really part of NAS, we kind of see it as potentially really being part of NAS, because at the end of the day, you could build your network with augmentation actually built into the network. And finally, this is bringing it all together. You obviously have the inputs, and the inputs are the data set that you have available to you and the metrics you want to optimize over. And they're the things we talked about earlier. So are we optimizing for accuracy, precision, recall? Also doing things like looking at how long it takes to actually run the network, how long it takes to train the network, memory footprint, all those sorts of things. And the idea here is obviously to have a process where you take all this data in, you have some sort of machine, and the machine chokes out at the far end an actual optimized deep learning network which solves your particular problem. So I'll now talk in very rough detail about the different NAS approaches. Obviously, you could take a brute force approach, and this is literally just trying every possible network that's out there. And this is computationally very expensive. And the original NAS paper talked about if you did this, it would take you 64 years of GPU time to actually generate every single possible network and train that network and produce results for how long you think that network would take. Now, interestingly, as a sidestep from this, there has been some work where people have been doing this sort of thing for things like the NAS benchmarks. Now, in the NAS benchmarks, what they effectively do is they do train every single network within a certain search space. And by doing that, they then provide that data for other people, so that if you have an idea for a neural architecture search approach, what you can do is you can try it out without having to do that computation yourself. So you effectively get a freebie in the sense that, rather than you having to do, oh, I'm going to try this network next, and then I'm going to have to train that network, you go, I'm going to try this network next, but I've already got the answer for how long that would actually take to run. And it also allows us to actually work out what is the actual best network within a certain search space. So on top of brute force approaches, there's ideas such as weight sharing. And in weight sharing, if you imagine for a neural architecture, you could imagine a super architecture which has every sub-network built into that network. So you would have every possible network size. So you'd have a network which was literally the size of the largest network, but you could construct any other network within your search space as a sub-network within that larger network. And the idea here is that we can reuse the weights when we've actually trained the network. So if you look at the figure on the right-hand side there, if I choose a sub-network, which is just the red nodes in there, then obviously I start off, I train my network. All of my different weights are currently unknown, and so I have to train all those weights. And as you can see, they're all in black at the moment, saying I need to train them. And then the W values are the values that I actually work out to be the weights for those particular networks. And so from that, we get our trained network, but then we might go, well, we want to try a second network. So we try a second network, and this time it's the new highlighted in red nodes. And obviously we've got some new nodes here that weren't in the original set of training data that we need to actually train up. But you can see the ones in magenta up here, which are now values that were from the previous run. And so we can kind of say we'll not bother retraining those, and we'll only train for the values of the new red ones down here. Now, obviously, if I picked a third network out of here, I would pretty much have covered every single possible weight within the network. And so most of them would turn magenta. And so therefore, you can train more and more networks without having to actually train the weights within them. You can just kind of use the pre-existing weights. Now, there's a huge, argument going on within the NAS community on this about whether or not this is actually a valid approach. It kind of seems to work in a lot of cases, but the big problem is that, you kind of think about it in terms of, well, if I use a different set of nodes within a network, there's probably a good chance that, the weights of those nodes would actually train to different values because I'm viewing different paths through the network. So yeah, some people kind of think it's a really good idea. Other people are kind of still thinking, I'm not convinced on this. But people seem to be getting some pretty good results out of it. So it's kind of gaining momentum at the moment. Next approach I'm going to talk about is differential architecture search. Now, with the idea with differential architecture is, imagine we've got, as in A up here, a set of nodes, and we want to actually have different operations between each of these nodes. And we don't know what's going to be the best operation. Is it an identity operation? Is it a convolution layer? Is it a pooling layer? We don't really know to start with. So what we'll actually do is we'll build every possible network structure within here. So the red might be a convolution, the green might be an identity in the red, and the blue might be a pooling operation. And we'll train that network. But then what we'll do is, if you remember, we talked about softmax, which allows us to identify the strongest item within a set. It gives you, for all of the different options, which one is the strongest. And so you kind of start saying, well, okay, for each of these links, which of these is the strongest result? Which one is giving us the strongest input into the network we want to actually get? And so you'll then start pruning away. So you'll start saying, well, in this particular case here, the best operation we could actually have is, I think I was saying it was the pooling operation. For this one, the red one, it might be the convolutional one, and so on and so forth. And this allows us to kind of peel away the operations that aren't particularly performant for us and just leave us with the ones that are actually quite useful for us. And so then we end up with a network which just contains a single link, which is the link which actually gave us the most performance when we actually started this process. But one of the big problems with this is it limits the network. If you imagine that you have every single operation on every single link within your network, that's going to take a lot of memory when you actually store it within your GPU memory. So you're effectively saying, I'm limiting the maximum size of network I can actually try this process on. The final approach I'm going to talk about is a quite modern and radical approach. And the idea here can we predict which network will provide the best results without actually physically going and trying that network? And the idea here is, can we look at certain characteristics of the particular system? And one of the characteristics is the expressibility of a network. In terms of a network, you can kind of think about it that there's only a certain number of regions a network could actually break your data space up into. And that might give you an expression of the expressibility of the network. You know, there's 5,000 possible things. Now, those things could change in shape and move around, but there's only, say, 5,000 of those. You can also think about the trainability, how easy it is to actually train the network to produce something. And then you can use those two concepts together to kind of give you an indication of which network is more likely to actually train and produce you good results. And so therefore, rather than actually building the network and training it, you just make a prediction, and then you might get it down to saying, these are the 10 networks I think are most likely to give me the best results. And then you could effectively go and train those and work out which one was the best. Okay, so that's a very, very short introduction to neural architecture search. And I'll now talk about how we think of the problems within these. And there's a lot of problems with current approaches. So the first problem is effectively what we call the few datasets problem. And that's because most NAS papers only evaluate their approaches on a small set of datasets. They turn on CIFAR 10, CIFAR 100, and ImageNet. CIFAR 10 is the one over on the top right here, and there's just 10 different classes, and they're fairly easy to distinguish classes. And ImageNet has a larger number of classes, but it's a very well-defined problem. Effectively, all of these are image-based. Now, I mean, there's no reason why neural architecture search can't be used on other data modalities, but people seem to be just sticking with that. And you might say, well, why is this a problem? You know, we go away, we use CIFAR 10, CIFAR 100, and ImageNet, work out which is a decent neural architecture approach, and then we just go and use it in the wild. And the problems come down to, these are highly curated and clean data sets, and they're not necessarily representative of wild data sets, the sort of things people really want to do. You know, I talk to people about doing, you know, problems where we do, say, bycatch of fish, and they want to find the best network for identifying, you know, the difference between cod and tuna or something like that. And that's a completely different problem to identifying the difference between cats, dogs, and aeroplanes. The other problem is, these three data sets we've been playing around with for years, and we kind of already know what the good results and good networks are for these data sets. And so effectively, are we just confirming our own biases? You know, we're building search mechanisms that, you know, it's kind of like, you know, I don't know, trying to train somebody to, you know, find a particular location in the countryside, and then realizing that you're effectively saying, well, the best place you can go is that direction. You know, so we're actually using all this extra knowledge that we've already got to actually understand how to actually train these things. And are those concepts actually generic to all problems, or are they just specific to the ones we've got here? And I'm just going to take a little sidestep here to say that small data sets and using repeated data sets is not actually just a problem of neural architecture search. So we did an analysis of the International Conference of Learning Representation from 2019, and we just looked at the papers that used particular data sets. Now, this is the papers that only used MNest, which is the data set in the bottom left there. 27% of the papers in the conference only talked about the MNest data set. Now, to put this in context, you've got to remember certain papers wouldn't talk about data sets, certain papers would just talk about theoretical approaches and not talk about data sets at all. If we talk about just MNest and CIFAR 10, that goes up to 40% of the papers. If we add in ImageNet, that's 43% of the papers. If we add in CIFAR 100, we're up to 44%, And then if we add in Fashion MNest, we're at 45% of the papers. And as I say, that doesn't account for the papers that wouldn't actually talk about data sets. So nearly half of the papers in this conference only talked about a small set of very curated, very specific data sets. And in general, I would say that we need to actually encourage people to actually try more novel data sets. I mean, I can totally understand why people would do this, because really at the end of the day, if you want to show your algorithm is better than somebody else's, what you really want to do is compare yourself to their data sets. But we really need some other more complicated data sets out there to help people out. So the second problem is what we call the restricted search spaces problem. Now, you et al. In 2019 found that the search spaces that people were using for neural architecture search were just far too constrained, and that almost every possible architecture they found within these spaces gave a good test accuracy. And effectively what they also showed was that often you could beat all of these NAS approaches by just doing a couple of random searches within the space and then keeping the best network that you found in that. And we kind of equate this to, so you can think about this like making some soup. If you've got a restricted set of ingredients, carrots, potatoes, salt, pepper, cream, and leeks, then almost any combination of those ingredients would be expected to give you a fairly nice soup. You know, it may not be the best soup in the world, but it would give you a fairly nice soup. But if you expand that search space and add other items in there, you can start imagining that you would end up with soups that wouldn't be particularly nice. And this is kind of what we're saying here, is that, you know, if you start off with a small search space of just good things, it's not surprising you get good results. Now, we're not just talking here about adding into our search space, you know, possibilities that we just know will be bad, because that again doesn't help us. But it could be, for example, you know, we now want to move away from just producing a soup. We now want to say, well, we can make different types of food here. And so one of them might be that you want to make a nice curry. Now, you know, the items that you would use to make a curry are within that set. They wouldn't necessarily make a nice soup, but they would make something else. But you could still make a soup. But depending on what your problem domain is now, depends on what you're actually going to do here. The third problem is what's called an evaluated search phase. Now, let's imagine you've just come up with this beautiful new NAS approach. You're getting fantastic results. You're beating everybody else in terms of the results you can actually get out of it. But part of that process was you made a new search space, and that could be the search space down here. So perhaps the blue here is what everybody else has been using for their search space, and the red is the new search space you have. We've got the problem here. Are the better results that you're getting due to the search space that you've created or the NAS approach? And that's one of the things that makes it very, very difficult to compare different neural architecture search approaches, because some will literally have a different search space and a different search policy. And therefore, it makes it very, very difficult to actually work out if one's the same as the other. And then the fourth problem is reproducibility. Now, this is a general problem in computing, you know, irrespective of whether you're talking about machine learning or not, which is the ability to actually reproduce the work from other people. Now, we defined this set of characteristics because what we discovered was when we actually tried to run other people's code, a lot of the times the code was broken, or it was missing parameters, or it was just, you know, it depended on libraries that were just no longer available. You know, we found one piece of code that required a library that had only ever been released as an alpha version, and it had been released individually to a particular group. And, you know, we were never able to actually get hold of that library because, you know, the manufacturers of that library basically said, well, no, we've moved on. We don't make that available to anybody anymore. And so we thought about it in terms of different things, such as code stability, as in, can you reproduce what was done? Is it bug-free? Is the documentation, is it easy to use and run? Is it standardized? And is it foolproof, as in can it go on and on? And as I say, many architectures just fail this. Right, so what are we doing about this? So we're hopefully trying to move people towards actually better work. And that's where I'll start talking about my interesting picture of will work for data. And it's kind of the realization that if we want to actually move NAS beyond just this toy example that people are using within certain environments to sort of build up new networks and so on and so forth, we need to actually apply it to real data sets in the wild. And it would be almost impossible for any researcher to actually collect all these data sets. And so I see this as a driver that people who are working in NAS should be working with other people in other communities. And it's kind of a win-win scenario here in that, we help them understand their needs for neural architecture, help them actually identify a good network, but it also provides us another good exemplar case of data that we can then use to actually identify problems with NAS approaches. So that's the first thing that we've been doing, is just literally going out there and trying to identify data sets. The second thing is to try and wean the community off the common data sets. And to do that, we've been running a competition, an unseen NAS competition. We've been running it at CVPR since 2020, but we're moving to AutoML in 2024, largely due to the fact that AutoML is a more natural home for where it's going to actually be. And what happens is the competitors have to produce a neural architecture search approach which would work on unseen data. So we don't show them what the data is going to look like. They just have to build their neural architecture search on the assumption that, without knowledge of what the data looks like, it can actually identify what's the best data. And for this, we've been generating various data sets. So this one is the language data set, and it represents words from different languages around the world. And the idea is can you identify what the actual language is? Now, the great thing about this is obviously it doesn't look at all like any of the previous CFAR datasets or ImageNet datasets, but it is an image dataset that people can actually apply their neural architecture search approaches to. We take other sort of ones which are quite simple, so we've gone for MNest again, but we've combined it into a novel way in which we're actually saying, well, each of the color channels is a different number, and each of those numbers, when added together, gives you the label. And other ones, such as taking the CFAR 10 data, but pasting 4 into the same image. Now, again, this is a way of actually creating novel and different data sets, but without us having to go out and collect huge amounts of data. Some of the later ones, we're doing that. And so we started off in the initial run of the competition, and we ran it in 2 phases. In phase 1, we sent out an architecture pipeline that people had to actually conform with. So it was how we loaded the data in, where the users put their own NAS algorithm, and then how we evaluated it. And then users could build that on their own computers. They could do their own training approaches. And then in phase 2, we took their architectures and we ran them on our computers with our data sets, which they had no idea what those data sets could actually be. And then we went forward from that. So in the first phase of the competition, our data sets were the ones over here. And one of the data sets was multiplying MNest. So instead of adding the numbers together, we multiplied them. Again, fairly simple, but it was quite effective. This one, I think, was a Project Gutenberg. So it was different books from the Project Gutenberg, and could we identify them? And then we throw in Fashion MNest just to see what people would do, given that you got a data set that they actually already knew about. All of our data sets would always look like image data sets, just because it's easier if everybody has a common grounding point for this. We kind of said that the data should have fair results if you ran ResNet 50 on it, and we used that as our baseline. We allowed up to 10 classes. And one of the underlying principles of this is the data sets were either very simple to solve if you know what they are. So for example, something like the multiplication MNest, if you know that that was actually 3 separate color channels with 3 separate numbers in it, you could very easily build a network which separated the color channels, identified the MNES numbers, and then took the 3 outputs and added them or multiplied them together. Or it could be really difficult. And we did one this year in the competition, which was aerial photographs of different places in the world. And you would struggle to identify where they were without actually any knowledge about it. So it's either really, really easy if you know what's going on, or really difficult if you don't, even if you know what's going on. So in the first year of the competition, there was the ResNet 50 results and what the record was from different competitors in the competition. I'll just skip on from there. And we got a load of raw results from this, and you can kind of see, obviously, some of them were quite easy to get good marks on, some of them were quite hard, depending on what the actual were. So then what we did is we actually adjusted these by actually scaling them so that a ResNet 50 score would give you 0, and then we looked at how far away above or below the ResNet 50 you were, because that then allowed us to actually add these 3 things together. And then we look at the evaluation we got from this. So unfortunately, most competitors focused on data augmentation rather than NAS. And this was effectively because a number of our data sets in the first year were normal image type images, and therefore data augmentation tended to work quite well. There was also a lot of competitors that when they went for the 24-hour run on our hardware, their code basically fell over. And that was largely due to the fact that, you know, they'd installed an extra library on their computer, or they required a certain setup or something like that. And also we had problems with the pipeline. Most competitions that are out there assume that the evaluation step is going to take a few seconds. You're effectively maybe doing some predictions from a network or something like that, whilst ours actually takes 24 hours. And that caused problems in that the fact that the networks would actually fall over. So we revamped this for 2022, and we split it now into 3 phases. We added a second phase in the middle, which was just a very short run on our computers. And this just allowed people to identify whether there was actually problems with their particular setup when they ran it in our environment. So, you know, they would run it, it would crash, but at least it didn't crash on their final run, and so therefore they didn't get a good competition result. They could then go and look at the output from that and go, oh, it's because we assumed that you had this particular library installed. We just need to add that into our thing to install that library. And we also try to encourage people to separate augmentation from the actual NAS approach, and which makes it a little bit easier to sort of see whether it's data augmentation or NAS, which is giving the best results here. So evaluation of 2022, the pipeline worked a lot better. By the time things got to the 24 hours, they tended to work unless the people had a little bit of a problem with their work. To say phase 2 worked quite well in knocking people out who had code that just wouldn't work in our environment. Unfortunately, it was a little too good, and some people gave up in that they never got it working from phase 2 to phase 3. So we didn't get enough results from phase 3 to be statistically accurate about the results. And we can also run ablation tests by turning on and off the data augmentation. We've just finished running the CVPR NAS 2023, and we got a larger number of competitors, because obviously we've been able to help them and support them through the whole process, and we're looking at the results from that at the moment. And just one bonus thing from this, our NAS competition pipeline allows us to actually put all these things together, but it also allows us to actually use this NAS pipeline independent from the competition. So one of the things we'd like to do in the future is effectively say, well, we've got all these competitors that have produced NAS approaches. We can make them available, obviously with the permission of these people, as a standalone tool that people could actually use for NAS. Other things that we're up to, so David is having a go at actually taking existing NAS approaches and seeing how they work on novel data sets, and that's an ongoing process. Mehmet has been doing, some of you may know Mehmet, is building some novel data sets. So he's been doing some work on the spec performance data set, and he's effectively gone out there and he's done a brute force NAS approach to actually produce every single, well, not every single possible network, but a huge number of networks. And so we're going to hopefully release that as a benchmark at some point in the near future to give people an idea of something that's not an image data set. So it'll be quite radical from that point of view. And that's just an idea of some of the results that he got out of that. Restricted search spaces, I'm just going to go through this very quickly. As I say, I've talked already about the problem of if you're doing a differential search within these environments, one of the big problems is the amount of memory space on a GPU you need for this. And so we came up with the idea of BonsaiNet, which allows you to grow the network. So you start off filling your memory up with what's effectively a single cell. So you put one of these in there. Once you've run out of memory, you then train that. It compresses down. Eventually you get to a point where you've got some space back on your GPU and you can put a second cell in there. You train that, it compresses down even further. You can get another cell and you can keep on doing that process. The other one is that we then thought, well, why do we need to have a search space? Can't we just have a network which grows organically within a search space? So you start off with an absolutely tiny network. And then what you do is you allow that network to mutate. You allow it to bring new connections in there. And by doing that, you effectively allow it to grow how it thinks it wants to grow. And we used the idea of train-free NAS, which was the idea of networks, which you don't train the network, you just predict what you think the results are going to be to decide where you want things to go. And you can kind of see from the right-hand side of the slide there, you get some quite organic and quite different and interesting networks, which are actually doing really quite well. Almost there, just final slide, reproducibly. We're doing some work here in actually trying to deal with the reproducibility by building containers that actually have these pre-existing approaches in them so that people can actually come back and try these networks for their data sets. Prove that code is actually working and allow people to do good comparisons. So finally, so NAS is a powerful mechanism for identifying good networks. It's easy to fall in the trap, though, of actually doing NAS for NAS sake. You know, we can do wonderful naval introspection where we just, you know, build up approaches that work on exactly the same data sets, but we really need good and novel data sets out there to actually test it in the real world. We need to expand the search spaces, and we need to develop approaches suitable for novel data sets. And of course, thanks to Rob, Mehmet, and David for their help in some of the work that went into this presentation. Thank you very much.
And thank you, Professor McGough, for this valuable time and for these valuable slides and presentation. Many thanks for your time.
You're welcome.
And we have two questions from well-known listeners. One is Mehmet Cengiz. Mehmet Cengiz has a question. I work on a similar topic to NAS, and my approach is more like manual brute force. What are the trade-offs between automated neural architecture search and manual design of neural networks, and in what scenarios is each approach more suitable in deep learning research and development? Can you summarize all the presentation?
So, I mean, it depends on the complexity of the problem, and it depends on how long it takes to train these things. So if you want to know definitively that you have the best network, then a brute force approach where you train every possible network, you come up with the results from those networks, and then you effectively say that network there is the one that gives you the best results. That's the best option you've got, really. But obviously that only works if it takes only a few seconds to train your networks, and you know the number of networks you've got is tractable to do this. Otherwise, you know, if it's going to take you, you know, sort of 50 years to identify the best network, well, by the time you identify the best network, machine learning will have moved on to probably something completely different. You know, we'll probably be doing quantum machine learning or something like that, and your results will be completely useless. So yeah, if you've got a nice small tractable problem, then going for a brute force approach is, totally legitimate and reasonable. If, however, you've got a big problem, yeah, you really need to be looking at some sort of intelligent way of actually identifying the best approaches for this.
Thank you. And from one more well-known listener, Ayşe Cengiz also has a question. Steve, how does transfer learning impact the efficiency of neural architecture search, and what strategies are commonly employed to leverage pre-trained models in the context of NAS?
Okay, so yeah, that's a good question. Something I was hoping not to.
You can also ask your questions in the course.
So transfer learning is obviously it's an approach where you take a pre-existing network, you have that network trained on some other data, and effectively that gives you a shortcut to getting towards a good answer for your particular problem. They're not mutually exclusive in the sense that transfer learning, you could do a NAS approach on a data set to get a good network. You could then do transfer learning by taking some data set and then once you've got that, moving on to the data set that you want to actually really do your problem on. Now, kind of where the boundaries between those two lie is not clear at the moment, and it's definitely an open research question, because at the end of the day, would you be better off doing a neural architecture search on one data set and then using the best network from that with transfer learning to get to your final solution? Or would it be better to do a neural architecture search on the data set that you want to finally move on to and then do, so on and so forth? And I think that's one of the brilliant things here, is that there isn't a clear answer yet to that problem. And, hopefully sometime in the next 5 years, we'll have an answer to that question. But at the moment, I think both approaches are very, very powerful and very, very useful. But obviously, which one is best, I couldn't tell you.
Yeah. And I have also a question for myself.
Yeah.
As you can also said in the previous slides, research should use old data sets to evaluate their new algorithms, new machine learning algorithms, or new models. And you are trying to find or trying to form new data sets for better algorithms, or for understanding new problems, or for solving new problems. But the researchers should use old data sets already to evaluate and to publish their models. How can we solve this challenge also?
So I think the problem is that if you want to get a paper published, you have to use the data set that everybody else has published. There's no point in trying to publish a paper which says, I've got a brilliant algorithm, I've applied it to a data set nobody else knows about, and I get 93% accuracy, because nobody knows whether that's good or bad. Whilst if you use MNEST, CFAR10, whatever, you can publish a figure that is very clear that you are so good for your particular approach. But what we need to increase the size of that pool of data sets. So it needs to be a case that rather than saying, here's 4 data sets and we always just publish based on those 4 data sets, we say, right, they're the 4 core data sets that you have to publish on. But now let's start building some data sets that are more complicated, more difficult to actually work on. So, it could be, so for example, telling the difference between a cat and a dog is reasonably easy. Telling the difference between a cat and a dog in an airplane is very easy. If you have a data set which is just breeds of dog, that's a much harder problem and much more realistic to what's going on in the real world. So what we need to do is encourage people to actually start using other data sets as well as these core ones. Now, interestingly, having done these NAS competitions for the last couple of years, we're now seeing people starting to use the data sets that we have used for these competitions as baselines for comparing their approach. You know, they'll say, oh, you know, our approach scores this high on the NNEST add data set or the CFAR tile data set, or all these different ones. So I think we are slowly pushing people in the right direction, but it's going to have to be in steps.
Yeah. Thank you very much. We saw that preparing or improving or developing new models are also important, but preparing new data sets are also very important for understanding new problems in the world, or preparing new solutions, preparing new and better and more efficient models. Thank you very much for your valuable time and for this presentation. I hope we will be together in next time. Thank you very much.
Brilliant. Thank you very much.
Thank you very much, and see you on the next session. Bye.
Brilliant. Bye.